Hello, everyone. This is Chris Kopak, immediate past president of APA. And this month, we're continuing our webinar series. One of the items that has come across very clearly through our recent member survey is that the webinars have been extremely helpful in giving back to our members that they can use useful information in running your universities, colleges, and our K-12 facilities. Today, I appreciate it very much that we have two local guys here in Tucson, Arizona, but they reach out throughout the entire country with water conservation measures. One is Damian Cox, president of EcoBlue. Damian, thank you very much for joining us today. And also Henry Johnstone, president of GLHN Architects and Engineering. GLHN is a firm here in Tucson that has been doing business for over 50 years. And Damian has the market, the North American market for the EcoBlue. So what we'd like to do, as always, we will be taking questions throughout the presentation. This is about a 45 minute presentation with about 10 to 15 minute questions. And with that, building and utility plant water consumptions. How do we in our universities, when our cooling towers are using in some cases 500 million gallons of water, in the desert here in the Southwest, we want to be extremely efficient with our water usage, but quite frankly, throughout the entire country. And both of these guys will be discussing that of creative ways and how we can look at our water consumption, how it is costed out throughout the entire country, and then also creative ideas to go ahead and be even more conservative and efficient with our water usage. With that said, we will have the presentation as always on a PowerPoint presentation. It'll be posted on the APA webpage, usually within a week along with the audio. And again, guys, Damian, Henry, thank you very much. We appreciate you taking time out of your busy schedule to educate our APA members. Damian?
Yeah, thanks, Chris, and welcome everybody, and thanks for taking time to join us today. Yes, I'm Damian Cox from EcoBlue, and I'm originally from Australia. I've been living in the US now since 2007, and as Chris said, our company specializes in indoor water conservation. So I'm going to hand over to Henry in a moment. I just want to walk you through the learning objectives of today's presentation, which is to understand the range of current and projected costs of water and sewer by region. And Henry and I are going to drill down and show you the water costs across the US in the various states and cities. And it's quite complex how water is priced in the US, and also the supply is quite complex as well. We're also going to review some data which is needed for a water audit for campuses. Henry and I have done a lot of work here with the U of A on water use on campus with metering and other calculators we've developed. And we've got an appreciation also of the relative magnitudes of water consumption on campus and what the high water using fixtures are on campus. And also we're going to consider current and developing opportunities to, as Chris said, to reduce water consumption on campus. So first, we're going to give you an outline of the complexity of water supply, particularly in the West. We're going to show a little video in a moment of water in the West, and I hope the audio is going to be good enough for you to hear. And then we're going to talk about the different challenges with community water cost and consumption, scarcity, costs and trends, and some of the unique features that university campuses have. And also, we're going to drill down then into the university campus water balance here for the University of Arizona. And then we're going to have a little brief summary at the end. So first, this is water in the West. This is a video, and I hope the audio is going to work. And Henry, if you want to chime in here.
Yeah, this is just an idea of how complex water supply can be. I think this is probably true everywhere, but certainly in the West. Kind of eye-opening little video here.
Seeing how one impact triggers reactions and triggers consequences in other areas, you begin to grasp a different understanding of the closed system. In the Colorado River, starting at the upper basin, we move the water out of the basin. Wyoming, we move it to Cheyenne. In Colorado, we go across the Continental Divide to the Front Range cities. Cross over to Utah. Central Utah Project takes the water all the way to the Wasatch Front. Come down to New Mexico. It moves it out of the Colorado River watershed to the Rio, to Albuquerque. Las Vegas uses it. 300 plus miles of Central Arizona Project Aqueduct goes to the central cities from Phoenix all the way down to Tucson. On the other side, it goes all the way to the coastal cities of Southern California. Because Metropolitan Water District of Southern California takes half its water from the Colorado River and half of its water from the Sacramento Bay Delta, they're connected. What happens in the Bay Delta matters in Cheyenne. It is one huge plumbing system that is intricately connected. When you start looking at the system in those terms, it changes your perspective.
Henry, you want to say a few words while we just getting the video off here?
Yeah, I guess the idea there was just, we often think as kind of consumers, users, you open the tap and water comes out. As you study this thing, it's just amazing how much is behind water supply. Certainly here in the West, but I think everywhere there are similar kinds of complexity.
Yeah, thanks, Henry. So that little video does show how complex water is, the supply of water is in the West, but also the price of water across the country varies dramatically. And this little chart or graph shows the different costs of water in various cities, about 30 US cities. And the little blue part of that pie chart is the actual water cost, and the green part is the wastewater cost. And a lot of cities, this actual wastewater cost is higher than the cost of water, and that's often due to the amount of energy and chemicals required in cleansing. If you cast your eyes up to the left-hand side of the map there where you see Seattle, you see they've got a very high cost of water, and then you cast your eye down to the southeast, you'll see Atlanta also the two highest costs for metro water in the US, and that's because they have to comply with federal mandates for underground storage, and they had to build new facilities. And the other big cost is Santa Fe in New Mexico. They've just built a big new pipeline there for the Rio Grande. So the water does vary dramatically across the country in pricing. And you'll notice in some of the Southwest areas, water is actually quite cheap compared to the areas where we have a lot more precipitation on the Pacific Northwest and the Midwest, and also in the North and Southeast. And this is an interesting little chart we found on increasing water and wastewater rates. This is across 50 of the largest metro areas in the country, and it shows the increase in water and wastewater rates since 2012. And you can see the trend there, that we're looking at rates in excess of 5% increases each year, dating back from 2012 to 2017. And here locally in Tucson, I've been living in Tucson since 2007. And when I moved to Tucson, the water here was cost combined water wastewater was $4 for 1,000 gallons of water. And you can see now from 2008 to 2018, that's more than doubled. And we're lucky enough to get the water rates that has been proposed here in Tucson through 2021. You can see that upward trend continuing with the cost of water and wastewater. And this is also an interesting little graph on showing the different costs of water across 3 cities. And we've got Los Angeles on the left-hand side. They've got a combined water wastewater cost for 1,000 gallons of just over $13. And if you move to the middle, you've got Seattle, which is around $25 for 1,000 gallons of water. So there's a huge variance there in the cost of water between Los Angeles and Seattle. And then we drop back down to Tucson, which is in the middle of the desert, and we got about a $10, just a little bit over $10 for 1,000 gallons of water here in Tucson. And what's driving these rates has been infrastructure debt and renewal. Supply, energy, and treatment costs has been increasing, and a lot of regulatory compliance now with clean water mandates. Pension healthcare costs have gone up for water workers, and security safeguards since 9/11. But the biggest driver, I think, has been drought and scarcity is what's been driving water rates upwards. And then Henry, you might talk about this.
So we figured that, well, there must be some relationship between the cost of water and the local consumption. So this is a little graph. Actually, I think this was part of a UN study. So it's a global graph that compares per capita water consumption with the cost of water, and it's almost exactly what you'd expect, this inverse relationship. The cheaper the water is, the more consumption there is, and you certainly see that at the bottom. The US and Canada, far and away the largest water consumers per capita, compared to somewhere like Germany, where the price of water is really high. Inevitably, that's a factor in the United States. We haven't seen a graph that's quite as demonstrative as this one, though.
Right. And just on that, Henry, it's a really good point. In Australia, where I moved from, the water in Australia was incredibly cheap, and we were very high consumers of water in Australia, and we would have been very close to the US and Canada. But over the last 4 or 5 years, they've put desalination plants into all of the major capital cities in Australia, and the cost of water has skyrocketed. So now our consumption in Australia is way down from where it was, and that's certainly has been a result of the increase in pricing.
Yeah, so this is an interesting little graph that shows, this is GPCD, that's per capita water consumption. And you see here, this is sort of a graph of time from the 1950 to the 1990. The per capita water consumption in the US was just monotonically rising. Around 1990, though, it started to level off, and now we're on a pretty steep decline over the last 5 years in per capita water use. So it really gives you some hope that things are changing.
Right, and that's a good point, Henry. In 1990, the reason that little trend line is heading downwards is in 1992, the US government brought in the Energy Policy Act, and all restroom fixtures were now rated and weren't allowed to use more than a certain amount of water per flush. So there's more water efficient toilets and urinals and hand sinks and shower heads around. So that's why that trend line is going down, and there's been a lot of advances in that technology over the last few years to continue that trend line. And that's the little red dot there shows the high point that where our water use peaked per capita back in 1990. And as I mentioned before, one of the big advances has been in restroom fixtures, and the EPA in the late 2000s brought in the WaterSense compliance and certification. So all the restroom fixtures now are WaterSense approved, and that's been one of the big drivers in reducing water use in toilets, showers, urinals, and faucets, etc.
So it's not only about cost. This is a couple of little slides here, sort of geography slides. This graph shows you by state what the per capita use is. And yeah, the water in the West, that video, those are among the darkest states highlighted there. 100 gallons per person per day was the aggregated number in 2015. And you notice the lowest water use is over on the far East Coast. Kind of surprising. You just would assume that water costs would somehow scale with temperature and precipitation, but clearly not in this case. The next graph we have just a couple other ideas about what the major factors are in water consumption. This is the ASHRAE climate zone map, and yeah, climate has a big impact here. A big portion of water use in hotter, arid regions is water-cooled cooling equipment. So air conditioning, more air conditioning you got, the more cooling towers you run, probably, as well as just your attitude toward water. If you go to the next one, we look again at precipitation, and this gives you an idea of where it rains. And clearly on the western side of the U.S., we're not raining so much, and that has a big effect on water used in irrigation and grounds. And so clearly that's a big factor here in addition to cost. So one of the things we kind of were fascinated by is we've kind of done this research on the global water problem and the regional water problem, and is the university a microcosm of what an urban environment is? And yeah, it is. It's pretty high density, high energy intensity, mixed use kind of a community, all within the fence of the campus. There are some differences, though. I mean, the resident population on a campus does not behave the same way the resident population in the suburbs does. The variable occupancy, certainly when the semester starts up, the consumption follows the school year. But one of the things I think is really fascinating is the opportunity that a university has, because it's got some centralized management control, its own utility system, to really do some strategic planning, investment, and to be able to really control how things are run. Here's a diagram that kind of depicts on a overall scale with the water and energy flows into a campus here. This is kind of the first of a couple of slides I've got on the water energy nexus. And certainly you've got a campus of the scale of the University of Arizona, 12 million square feet, and you've got to pump a fair amount of natural gas in there to run the heat, the gas turbines. You got to buy some electric power, and that combines with the output of the turbines and runs the chiller plant. In the Sonoran Desert, the chiller plant is a major, almost life safety kind of a feature of our campus here, keeping everything cool. So we have to put power into that. But in order to run the chiller plant, we've got to evaporate water in the cooling towers. Ultimately, all the heat that's pulled out of the buildings gets rejected through evaporation at the cooling towers. What we get here in our area, and I suppose many areas along the sort of southern half of the U.S. where there's a fair number of cooling degree days, is the amount of water we spend for evaporation in the cooling towers is equivalent to the amount of water we're spending in building use and in irrigation. Many universities have embarked on water master planning. Here's a couple, one at Stanford, one at Yale that I looked at, and these were done a decade ago. These were done quite some time ago. It's just a rational planning process. First, start with metering, collating data, auditing, analysis of the data, really figuring out, getting arms around where the flows are at any given time, coming up with alternatives and evaluating the economics of those alternatives, and then implementation. And ultimately, I think in at least these two universities and probably others that have gone through this process, the end product is not just we implemented and we're done. It's an ongoing monitoring, improving, monitoring, metering, trying some other stuff. It's kind of an ongoing process ultimately. So I wanted to put this up here. This is the famous Lord Kelvin, and this has been quoted many different ways, many times. I found the original, this is what he actually said from the Institute of Civil Engineers. And I just want to bring your attention. Certainly, this is a thing that says if you can't measure it, you can't manage it. That's the simple version here. But I really like the part that says if you can't express it in numbers, your knowledge is of a meager and unsatisfactory kind. So fundamentally, in order to do a project like this, in order to conserve water, you've got to understand what the flows are, what the values are, what parameters you can compare against each other.
Could you say that again? That just sounded so good. I got
your knowledge. Yeah. All right, go ahead. Okay, so we're just going to talk briefly about the University of Arizona, and we're really just using this as kind of an example of a typical campus. So certainly, water is a big deal here, but the part of the campus brand, part of the student experience, has to do with how water is used. So irrigation is indeed a big part of this. Must maintain the spaces that attract people. This university, 390 acres, something like 12 million square feet, and the primary uses of water, which I think this is probably true everywhere or most places. Irrigation, buildings, and cooling are the fundamental uses of water. At the university, now the university enjoys having some groundwater, a mixture of produced water coming out of the aquifer directly below them. So there's a series of 7 wells, and they purchase water from the public utility. That's Tucson Water and the groundwater, the blue and the red. Reclaimed water, there's a fairly significant reclaimed water system in our community here, and so university purchases a lot of reclaimed water, almost entirely for the use of irrigation of grounds. If you look at the graph on the right, then you get a sense of how that water is distributed. And I just bring your attention to the green and the purple, green being evaporation, annual evaporation in the cooling towers, purple being annual blowdown. We'll talk a little more about that. But the two of them together are over 50% of the total amount of water used on campus a year. There's been a series of improvements here, probably the last 6 years when this started to track this thing. As I say, one of the first steps was to bring in better measurement and metering equipment and systems. So then now there's a fairly sophisticated SCADA system on all the wells and the points of purchase from Tucson Water. There are domestic water meters in most of the buildings, certainly all the large buildings. Those are now all up and running and calibrated, checked, working well. That's been a big part in the irrigation department. Fairly significant investment in a new irrigation control system, kind of a head end, and devices out in the field. And then again in the plants, a major effort to improve plant metering and be able to really get real-time data on all kinds of parameters involving energy and water. So in irrigation, just briefly, most of the irrigation, well, first point we wanted to make is sort of an obvious question is, well, why can't we just harvest the water that falls on campus? That's really an interesting question in a place like Tucson where it really rains just about 2 times a year. One of them is right about now, monsoon season. We get about half our rainfall, and the other half comes over a course of 2 months in the winter. So although we have the potential to collect 120 million gallons, which would be about 20% of the total, water consumption here, the practicality of collecting that volume of water and storing it for use is just really difficult. So we are able to, in sort of a building by building scale system, put in cisterns, and there's a number of projects where that's proven to work okay. But just as a theory of why can't we collect all our rainwater, pretty challenging engineering problem and would be financially quite expensive. So instead of that, we do a lot of xeriscaping. There's cactus. That's a great thing for low water use. Go to the next one there. And then certainly the reclaimed water used in irrigation for relatively small but very well designed, established and maintained planting areas and turf areas. Most of the athletic fields are on reclaimed water, not all. But that's kind of the overall, wherever we can use reclaimed water practically for irrigation, it is used.
And moving across to our building water consumption, I want to just run through a couple of case studies we did here at the university. One was a residency hall, and we found here that there were 7,000 students in the residency halls on campus, and their domestic water use is around almost 3.8 million gallons of water per year. And this is a little pie graph showing where the water's indoor water use by Fixture. And you'll notice that showers is the highest water user at 63%. We were able to go in and measure the water flow through the shower heads that they had installed in their facilities. And I'll come back to that in a moment. But we also were able to look at these residency halls on campus. They implemented throughout the 2000s some pretty aggressive water efficiency initiatives, and changed out toilets and urinals, shower heads, faucets, etc. And you can see the little blue bar on each one of those shows the water use in hand sinks, showers and toilets before the change, and what they were able to achieve after they went through and did implemented these water efficiency initiatives. And then in 2018, they can even go further with their water efficiency, and because of the advances in technology. And the big water user was showers, as I mentioned. So here we just put together a little calculator on shower heads, and across campus there's 7,000 people showering once a day, and they currently had 2.5 gallons per minute shower heads. And if they reduce those down to 1.5 gallons per minute, they would save around 15 million gallons of water per year. And the overall water and energy savings is about $400,000. But the big item you want to focus on is the water heating saving, and that was almost $380,000 in savings if they move to these water efficient shower heads. So whilst the water saving is great, the heating and energy savings is even greater. So just encourage everyone that's out there and has res halls to look at their shower heads, because they're a very easy way and simple way to conserve water and doesn't require any behavioural changes by the users. We're also able to look at the restroom water use by Fixture on campus, and you'll notice here that, and we want to just focus on toilets for a moment. 46% of the total water use was in female toilets, and obviously you'll notice that in urinals there's only 20% of water use. And for females, they don't have an option as the guys do to go in and use a urinal, so they have to use a toilet. So it's the same amount of water that's used each time they go to the toilet, whether it's for liquid waste or solid waste. And one item which I like are these dual, which doesn't require any behavioural changes, are these dual flush handles, which you may or may not be familiar with. So with these particular handles, they're a simple retrofit, and they can reduce water use by 30% for liquid waste when you push the handle. In this particular unit, you push the handle down. There's two of these different flush units available in the marketplace. One of them is what they call the uppercut, and you actually pull the handle up to get the liquid waste, for liquid waste, and to get the water saving. And they did a behavioural study on these units at the University of Missouri, and they found that in 2 buildings they had installed these units. One where you had to pull the handle up for the liquid waste, and the other building they installed units where you got to push the handle down. And they found that in the building where they had to pull the handle up, because it was someone's normal behaviour and pushing a handle down, they only got to achieve a water saving of 12%. But in the building where they're working with a user's behaviour and they're pushing the handles down, they achieved a water saving of 30%. And then this is just a sample project we wanted to walk through with a building that had 20 non-efficient urinals and 20 non-efficient toilets. And we've got with 2,000 students, and wanted to look at the difference in dollar cost and return on investment for a university here in Tucson, for example, compared to a university in Los Angeles, compared to a university in Seattle. So you'll notice that the university in Tucson, which has the lowest cost of water, they're roughly going to save around $26,000 a year in cost by replacing non-efficient urinals, non-efficient toilets with water-efficient models. And in Los Angeles, up around $36,000. In Seattle was almost $70,000. So the project summary, we can reduce water use by changing out these old inefficient fixtures to water sense units. They want to save in that particular building around 2.67 million gallons of water per annum. And the capital outlay was fixtures and installation was around $20,000. Now in Seattle, because their water cost is so high in Seattle, their annual savings per year is about $67,000. Return on investments around 330%, and the payback is 3.6 months. In Los Angeles, it's about $36,000 a year in savings, and return on investment around 184%, and 6.5 months to pay back the initial investment. And in Tucson, where we have the lowest cost of water, the return on investment is around 134%, and about 8.9 months for payback. One thing which I didn't include in these calculations was that all of those cities, all the water utilities and water conservation departments in those cities offer rebates. And if we included the rebates in those calculations, the Seattle would have had their return in about just over 1 month, about 1.5 months, and in LA they'd be paid back in about 3 months, and in Tucson it was about 5 months to pay back the overall cost of that investment and project. So I'll move over to Henry now for building meter data.
Right. I just want to tag on to what Damien said there. The reason these paybacks are looking really attractive is because the price of water is going up. Right. So a big incentive here to actually start doing stuff that for the last 20 years we've known was available, but maybe not worthwhile doing. Now it's worth looking at. Maybe it's going to be a financially attractive kind of a thing. So these are just a couple of images just representing the kinds of data we're able to now collect from University of Arizona buildings. That's 3 different dormitories, Likens, Coconino, and Kaibab Huachuca. They're of different sizes, different ages, different technologies. Here's a graph when you normalize that by the number of beds, so that's water use divided by bed count. Now, there's a couple of erratic things that happen in the summertime there, but if you look during the school year, September to October, January through May, it's pretty remarkable that the per capita student water use is very similar dorm to dorm to dorm. It may have to do with the fact that there was a water fixture renewal program maybe 5 or 6 years ago. So they're all running on the same kinds of technology and fixtures.
And that's right, Henry, because we did a walk through all those residency halls, and they had identical fixtures for toilets, hand sinks, and shower heads, which they all upgraded in the late 2000s. So they're all very consistent. But
even now, even though that was just a few years ago, more recent technological change in shower heads, you could take another 25% out of this if you swept through there and changed out all the heads. So then another image is just one particular building, looking at it over a number of years. And this one's kind of interesting because the behavior changed from the first 2 years to the second 2 years. The kind of thing you could really evaluate building by building, a trend analysis. I think one of the things, behavioral things, we've seen a lot of case studies where competition in residence halls for water use is actually an effective way of reducing the shower times and reducing water consumption as a whole. And if you've got this kind of data, this can be real time on a screen in the lobby, and the students perhaps will pay attention to it. Just another couple images here that I think are fascinating. This is the kind of data you get real time looking at a water meter over a course of a week or two. This is again a student dorm. So look at the real high point there where it hit about 1,000 1,000 gallons, a kgal, which is on April 6th. That little spike, if you dial in one level more, that's about 5 o'clock in the afternoon, and this is a Friday. So you can tell they were all gearing up for party night.
So Henry, that's actually hourly data. So that is great to track leaks and anything that's happening inside the facility?
Absolutely. Yeah, we've seen cases where you first look at the monthly data and say, wow, this building is behaving different this February than it did last February. Then you auger into this level of detail and say, I see why that is. There's some valve not closed. There's a leak. And you can really see it hour by hour on this data set. Good. Another example, that was a dorm. This is a big rec hall where, again, a lot of students go to shower. Okay, so I want to move into utility plants here. University of Arizona, like most universities, has some kind of a central utility system. Here, there's 3 large central plants, central cooling plants. 2 of them have steam boiling systems, and 2 of them have cogen. So it's kind of a mixture. But the utility, the water consumption is really focused into the cooling towers and the boiler makeup in these plants. Which is the condensate makeup, with primarily that's RO, the boilers are fed with RO water, and so there's a fair amount of blowdown water there. There's a fair amount of water going into the RO system. Chilled water makeup, it's a closed loop. Why would that be a water consumption issue? Well, when you got a leak and it's underground and nobody knows where it is, and it goes on for a while, that's a challenge. That's a water consumption challenge. Having the data, though, sure lets you figure out exactly when it started, what do you got to do to stop it. We used to see a lot of bearing cooling, a kind of direct use of water just once through. I would say in the last 20 years, in the kind of university plants I've been in, not very many open water drains the way they used to be. The big load of, though, is the cooling towers. So I thought I'd just kind of briefly go through the methodology to figure out what the ratio of water is, the water rate of a cooling tower, just to review this kind of thing. So if you had a 15,000 ton cooling load, a plant that's taken 15,000 tons out of the campus, the cooling effect is 180 million BTUs an hour. If your chiller was 0.5 kW per ton, that's a pretty decent chiller in today, a chiller you might buy around now, particularly on a hot day, able to do 0.5 kW per ton, not bad at all. That would correspond to 7,500 kilowatts into the chiller motor, or the energy in, if you convert that to BTUs, is 26. So the total amount of heat that you're pumping out of the cooling tower is a combination of the heat you're extracting from the campus plus the heat of compression, the energy that you're putting in to the chiller to get the heat out. So that turns out to 206. Now, if you convert that total amount of BTUs we're dumping out the cooling tower into water, that turns into the 24,000 gallons an hour to get 15,000 tons out. The other factor, though, in a cooling tower is the cycles of concentration. That's the amount of water you've got to draw off it, continuously draw off it, to keep the concentration of solids that are in the makeup water from building up to a level where they're gonna affect the efficiency of the chiller tubes. This is really the core of the energy-water nexus of a chiller plant. Is if you aren't spending enough water to keep the purity up, you scale the tubes, and so you're trading water on one side against energy efficiency on the chiller on the other. So at the bottom of this thing, you look at this, at 5 cycles, that represents 25% of the water you're evaporating is now being wasted in order to hold a 5 cycle. Pretty typical in the Southwest anyway that we run at 5 cycles, maybe a little lower than that, which gives us a total makeup rate of 2 gallons per ton hour, which is kind of an interesting number when you think about gallons of milk and ton hours of air conditioning. It's a fair amount of water that you don't see. It's invisible, not really an obvious part of air conditioning. One other factor, I'm just doing a simple energy balance here. There really is an efficiency factor on a tower. So ultimately, it's going to be more than that. There are other reasons why we're subcooling the discharge air. All right, go to the next one here. I don't want to linger too much on this, but the cycles of concentration thing always kind of bugs me, how much water we've got to waste in order to evaporate. And I stuck the little formula in there to figure this out. Again, we often think of, or I used to think of, 5 cycles of concentration as being a reasonable number. And what that means is if you've got, let's say you've got 50 parts per million of silica in the incoming water, and you're trying to control your cycles of concentration or your silica level in the chiller tubes in the recirculating flow to say 150 parts per million. Well, the cycles of concentration you need to achieve that is 150 divided by 50, or 3. So that's the kind of thing that you got to really pay attention to if you're the chiller plant operator and you're trying to keep your tubes from fouling, which represents not just a maintenance problem, but really the key thing is it's an efficiency problem. It's directly correlated to electric energy. Okay, so let's move on. This is kind of a surface plot. This is if you look at this thing, ton hours. That's the load is in the vertical dimension. We've got the time of year in the horizontal dimension, and the time of day. So this is a surface plot of the cooling load of a campus. The U of A looks a lot like this. Came from their data. And so you see on a peak day, the very spiky tips of these little mountains in here, that's the peak demand. That's where we get to see something like 30,000 tons on the hottest day of the year here at the U of A. If you look at the volume under this surface, if you thought about that as a big surface, what's underneath it? Well, that's the total amount of ton hours. That's the total cooling load we're pulling out of the campus over the course of a year. And that correlates almost directly into this campus water utilization. Every ton hour here represents 2 gallons of water. So that's a fairly simple, there's some simplification here. It's a little more complicated than this, but fundamentally that's how we get to, of the university's 550 million gallons a year, the cooling towers are consuming almost 300 million of it. Okay, so now I want to sort of set the stage. This was a graphic that we developed to try to visualize the energy-water nexus. So what we've got here, Sankey diagram, the width of these lines corresponds to the units of energy. And I got everything in energy, which is a little odd. I'm converting cubic feet of water into BTUs. And I'm just doing that strictly by the fact that there's 1,000 BTUs per pound of water. The latent heat of water is 1,000. So there's a way to just say, hey, water equals energy and certainly from the standpoint of the central plant, that's what we're using it for, taking energy out. So this is a graph that's showing both the energy and the water flows, starting at the utility power plant down at the bottom there. So you're seeing fuel input on the far left, the brown there. The fuel converts into electricity being the red. At conventional power plant, it's about 40% efficient. So 60% of the energy, one way or another, is leaving the power plant through cooling towers or through the stack. The other 40% is the red line going up to campus here. On the water side, then, it takes an equivalent amount of energy to dissipate the plant in the cooling tower. So you can kind of get a sense of the amount of latent water in energy in looking at the bottom of this graph. Okay, let's go to sort of the blow up here. Go to the next slide. Yeah. All right. So then I blow up. Here's the campus itself. Those 2 dotted boxes. And there's the red line. That's the power coming into campus here. So we look at that as the power coming into campus goes 2 places. One of which is going to the chiller plant. That's running the chillers. That's running the towers and the chillers. On the other side, it's really feeding the internal loads of the buildings. That's the lights, the computers, the people, or not so much the people, the elevators, whatever the electric demands are in a building end up being heat loads for the building air conditioning system. You see over on the far left there, the other components of the heat load, the envelope, the people, the ventilation. So all of those combined are the energy we have to pull out. And you can see in the gray line there, that's the getting to the chiller plant. That's the amount of energy we're pulling out. Ultimately, those 2 combine. We talked about that. and we dissipate it through the cooling tower. On the blue side, you're seeing a little line there, that kind of little U-shaped line draining down. That's the blowdown. So if you hit the button here, two key parameters in this: the coefficient of performance, how efficient your chiller plant is, gives you an idea of the ratio of how much electric energy it takes to pull the rest of the heat out of this thing. On the water side, the cycles of concentration is the ratio of the amount of water that you're blowing down in order to keep the chillers efficient. One thing I really want to make a point here: there's this close coupling between energy efficiency and cooling tower water use. The less energy you're extracting out of campus, the more efficient your buildings and distribution system, the more efficient your plant is, the less water you have to pull out of this thing. And where in the past we've always kind of looked at energy conservation measures on their own kind of standalone thing, really there's a water component here. And as the price of water gets higher, we really need to start to think about what's the water savings in an energy conservation measure. Okay, so here's just a quick comparison. That's a water-cooled. We just talked about that. If you hit this again, this is an alternative, which would be an air-cooled system. Interestingly, I always assumed as a mechanical engineer, hey, the water-cooled central plant is going to be so much more efficient than an air-cooled system that it always makes sense to do it. And most of the time, it really does. And on the university setting, maybe that's still always going to be the case. But what you see here is if you had a 0.5 kW per ton on a water-cooled system and a 0.9 on an air-cooled system, you can see, yeah, we're using a lot more electricity on the air-cooled system, but the effect back at the power plant isn't as significant as you might think. So yeah, we're using more water in the case of an air-cooled chiller back at the plant, but it's not enough to compensate for the amount of extra water we're using in an air-cooled system. All right, that was my little Sankey diagram. So another thing that I think is really interesting and a trend we're seeing here is if you start to now look at the ratio of water cost to electric energy cost in a chiller plant. And this graph is giving you an idea of what are those costs for a 1,000-ton plant. Certainly the air-cooled plant doesn't care, independent of water, but a water-cooled plant, the higher the water cost, the more overall cost that's going to induce. Yeah, 5 years ago, it was a slam dunk. It's going to be a water-cooled plant every time. We're now approaching, as we get water rates getting into the $7, $8, $9, $10 a CCF range, we're starting to approach the place where if you just do a direct comparison at our electric cost and our water cost, you'd say, woo, it's almost cheaper to do air-cooled. EIA, the federal agency that looks at this stuff, is projecting electric costs over the next 20 years to be relatively stable and water costs to be increasing. So this is something to pay attention to. All right, I'm kind of rounding the clubhouse turn here. What are things we can do to improve water consumption in cooling towers and on campus? Well, certainly working on the cycles of concentration, which involves more sensitive control, more attention to chemical treatment. Maybe there's a way to eke out a little more out of your water treatment guys. We always wonder why we can't use that blowdown water for some other valid use. Problem is it doesn't grow green grass very well, and there isn't a heck of a lot else you can do with it. So I talked about reducing the cooling load, big effect. And we've talked about air-cooled heat pump. Stanford University converted to heat pumps, made a big impact on their plant water consumption because their cooling towers dropped off quite a bit. But I want to just kind of end with what are our opportunities here, at least in our region now, which are cascading. We're using non-potable water instead of domestic water for running the cooling towers. So again, another Sankey diagram. This on the left is showing the inflow to campus here. And you see it splits two ways. One way it's going to potable water to the buildings, and then that comes out as water going to drain to the sewer, showers, toilets, urinals, all that kind of stuff. That's going to the drain. I gotta go back up. And then the other half of it splitting there, you see part of it going down. The purple at the very bottom is the plant blowdown. The gray that's poking its way up, that's the evaporation. All of this, with the exception of the evaporation, is going to the county sewer system now. The opportunity is to recover that water, treat that water at the county sewer system, and pump it back onto campus. And that's going to represent it, since we use about half of our water is cooling towers. If we could use reclaimed water, that would cut campus domestic water in about half. So one way to do that, we talked about that we're lucky enough in Tucson to have a fairly large reclaimed water system network through campus. Well, we can connect onto that and not insignificantly figure out how to manage the chemistry of that water in an effective way that doesn't ruin the heat exchangers. That would be one way to do it. Another that we've seen elsewhere, Emory University has one of these setups here. This is a local water treatment plant right on campus here that's collecting liquids from wastewater, processing it to the point where it can be recycled in a cooling tower. So finally, the silver bullet. This is what COPAC always wants is, give me the silver bullet here. The one thing that's cheap and easy and will solve all my problems. Well, that's really hard to find.
It has to be efficient and cost effective.
That's really hard to find. But one thing that I've certainly thought about, and maybe many of you have, is, well, why can't we somehow just collect the moisture that's coming off the top of the cooling tower and drain it back into this thing? It's almost like a perpetual motion thing, but it seems like there should be some potential to do that. And that's it's been out there for quite some time. What I found just a month ago was there's a student group, actually, some kind of a student research project at MIT, where they figured out that if you shoot ion beams into the plume, you ionize the small droplets, or maybe it's even smaller than that, you ionize the flow, so then now it's attracted to that screen, and if you design the screen right, it somehow flows off there.
Are you making this up, Henry?
No, I'm not. I'm just these kids at MIT might be, but so all I wanted to leave you with is I think there's a lot of R&D going on, and some innovative idea like this might actually work and might actually catch hold. Okay, so we'll summarize here. Yeah, again, as the water rates go up, this is probably a good thing from the standpoint of water consumption, because it really does drive efficiency and innovation. We've seen many successful examples where a rational planning process on a campus, get your arms around the data, figure out alternatives, look at the economics, implement, that actually has proven to work pretty well, and we think that's really the way forward for a university.
And also now there's a very attractive return now on investment, and mainly, as Henry mentioned before, due to this increase in water rates that's happened and is going to continue to happen over the next few years. So it's very attractive now to do invest in water efficiency fixtures, and also a lot of the water conservation and water departments have water conservation teams which run programs which provide really generous rebates now for high efficiency fixtures. They drill down into cooling towers, and they also have some nice innovation credits now if you're bringing water efficiency, and a lot of the water utilities are giving rebates for innovation credits. And also, we believe that on our campus domestic water use, you can reduce your water use up to 50% with all of the advances now in technology with restroom fixtures and efficiencies, etc. So over to you, Chris, for any questions.
Well, there is. I'll tell you. And thank you, Damien. Thank you, Henry. A lot of information, a lot of detailed information. While we're going through questions, because they're coming in, we're not going to have enough time. But if you do have questions, go ahead and send them to us. If we don't get them to you, we'll go ahead and answer them and then send them on our Apple webpage. And maybe we can put that slide up too about the metrics as we're going through the rest of the questions.
Okay. And
so we do have GLHN and EcoBlue doing a detailed water conservation review of our 11 million square feet at the University of Arizona. One of the questions, it relates to the silica. And you talked about silica into the water systems, into the equipment, and the negative impact on that. Can you go over that again a little briefly, and also possibly the turbine? Could it get involved in any of your turbine at all?
Sure. Yeah. Silica is a dissolved solid in the incoming water. So we experience that here in our water stream. It's not really a problem unless it gets to a concentration of something on the order of 150 parts per million. And I got to say that a little cautiously. In the chillers that we have running with refrigerant temperatures and that we are running at 150 is about the number, where if you get above that for much time at all, it starts to plate out on the tubes. So it's like a critical thing. It's going to plate out at 150. The incoming water is pretty consistently in the 25 to 35 range. So that what we have to do in these cooling towers is continually blow off water so that the recirculating stream that's going through the chillers doesn't get over that 150.
That's perfect. We're going to do this rapid fire. We have so many questions coming in. As Thomas Williams mentioned, the video at the beginning, he believes it came from Beyond the Mirage.
Yeah, that's right.
And so there's a movie on water called Beyond the Mirage. You can go ahead and Google that, YouTube it. We also have a question that comes about blowdown. And this is from Ian. And so, Ian, good hearing from you. How do you blow down rate? How do the blowdown rates vary with water quality, hard, soft, neutral makeup?
Absolutely, it's a great question, and that really is at the core of this. I think we used to, when water was cheap and we didn't care, you'd have a manual valve, and you just over time figure out how much you had to open that valve to keep the tubes from fouling. And there was really no science or physics or engineering behind it. It was just, let's keep bleeding off water, kind of the way I do my evap cooler at home. But as time's gone on and as it's become more critical that we manage this blowdown, we do it a number of different ways. Probably the most common way is conductivity. You look at the electrical conductivity of the water stream. That correlates to the amount of calcium that's in the water, and therefore indirectly you say, well, if the conductivity is this, that will correlate to a dissolved solid value of that, and that's what we're controlling to.
Excellent. We're going to have a question on rebates here in just 1 minute, but another one regarding our utility plants from Christopher Radmansky. How does the campus balancing tower cycles of concentrate with the Legionella risk? Which is a big concern. And FYI, go to our APA webpage on our webinar series. We've done a series just on Legionella, a whole presentation.
Yeah, and Legionella is another whole animal in and of itself. Blowdown is an important, to keep the dissolved solids down, blowdown is important. I think in controlling Legionella, there's a number of other factors. Actual solids in the tower make a difference. The amount of iron in the recirculating water makes a difference. I probably don't have enough time to really get into this thing, but it is a quite complicated chemistry and physics problem to balance all of the chemistry and do that cost effectively.
Excellent. Damien, if you can, I know we have Adam Polak on the line here too, and we appreciate it. We got hundreds of folks, so this is an excellent topic, especially coming out here from the desert and the Grand Canyon, Colorado River, and how important that is. Rebates and being our water conservation. Talk about that just a little bit more, what the universities need to look at.
Yeah, sure. So good question. So with rebates, it varies from water utility to water utility, but essentially here on the West Coast, all the water utilities, or most of the water utilities, are offering rebates for commercial toilets, so high efficiency water sense approved toilets, and that varies from $250 per toilet in somewhere like Los Angeles to $100 in Seattle. Here in Tucson, that's $150. And then for urinal systems, for water sense urinal systems in Los Angeles, that is $500 for a urinal, a water sense approved urinal in Los Angeles. Here in Tucson, that's $200. So the rebates do vary from place to place, but there's some. You can go onto there's a website which tracks all the rebates nationally. So I'd encourage you to check on that website. I can send that website out, Chris, later on if they need it.
Excellent. And Henry, if you would, what about water master plan? Comment on that, because that's critical to have a detailed master plan in place. Sure. A water master plan.
Yeah, sure. That's I think the first step is to decide that you're going to plan this thing. And sure, it starts with the Lord Kelvin statement here. It's going to be really hard to plan stuff unless you have granular information on what the consumers are, what are they using it for, how much of it's going to waste, and when these events are occurring. So certainly a water master plan really best starts with, we've got a metering system in place, and we've got some confidence that it's going to go. Then you integrate in, all right, now let's look at some more global kinds of information. The idea of our cooling load, for example, or our steam load. Really get down into that and correlate that with water consumption. Ultimately, you get to a point where you say, okay, I know where the problems are. I know where we've got the biggest opportunities. Now we get into a kind of high-level engineering of evaluating alternatives. We can look at the economic benefit of changing out toilets versus changing out shower heads. We can look at the economic benefit of working in residence halls compared to administrative buildings. Really come up with a tight list of priorities, and for each priority, an idea of what the ROI is, because ultimately none of this is going to happen unless you've got ROI.
And if we can here, we got about 5 minutes left. Damon, you talked about Australia, your home country, and how, if I heard you correctly, the water consumption has dropped.
It has. Yeah.
What caused that? What led to that reduction?
Yeah, no, good question, Chris. So in Australia's got a very similar layout to what's happening here on the southwest and the west coast of the US, where we have a major river that provides all of the agricultural states, similar to the Colorado River. And we had a huge drought came through Australia in the early 2000s, mid 2000s, which caused massive water shortages, obviously, and also pushed rates up, but also forced a lot of the water utilities in these major metropolitan areas to improve infrastructure. And the major thing that all the cities did was put in desalination plants. And the desalination plants were hugely expensive, and water rates went up accordingly. And once water rates went up to the levels they are now, like when I left Australia in 2006, water rates were very similar to what they were here in Tucson when I arrived in Tucson. So it was about $4 for 1,000 gallons of water in most of the metropolitan cities in Australia, or major capital cities, I should say. And now those capital cities in Australia, their water cost is very similar to the cost of water in Seattle, which is like $25, $26 for 1,000 gallons of water. So the cost of water there has increased almost 5 times from where it was, and that's driven people to conserve water purely and simply because the economics of water is so expensive now. And that's the trend that I've been seeing in the US since I moved here, where water rates are increasing.
So as they're increasing, one of the questions comes in from James McMullen, and it goes back to that first slide, one of the first slides about Seattle and looking at the country as a whole and the high rates. Why exactly, again, is Seattle sewer costs so high?
Right. Yeah, good question. So in Seattle, their wastewater treatment process is very expensive because they have an outflow that goes out into the Puget Sound, and the water has to be treated to such a high level for it to be going out in the Puget Sound to protect their fish population off the coast. So the wastewater treatment cost there is very expensive in Seattle, as you saw, and also in Portland and Oregon, they've got a very high wastewater treatment cost as well because of that reason.
Well, we like eating fish, and we want to make sure that's healthy, so that's for sure. A couple other quick questions here, and this is from Adam Keeling. Henry, is there a source for water use intensity benchmarks based on building use type?
There is. In fact, there's a university source whose name is STARS. Right. Yes. And there's a website that actually, I don't know how accurate or often it is updated, but it is very interesting to compare campus to campus.
That's a good question. So the Energy Star Portfolio Manager through EPA, they have an energy use intensity metric, and they're also developing a water use intensity metric as well for buildings. So at the moment, it's only available for multi-family buildings, but I know they are developing the program to include other buildings as well.
We're going to run out of time, and we probably have 20 more questions, so excellent topic. This is about reclaimed water, and I know here in the Southwest that reclaimed water for irrigation is critical. What about the use for irrigation using reclaimed water, or using blowdown for irrigation, and then also using reclaimed water for cooling towers?
Yeah, I think the first question, can you use blowdown water for irrigation? The problem is we've seen demonstrated a number of times, but certainly when we've talked to landscape architects and botanists, the real problem is the salt concentration in the blowdown. We're blowing it down because it's concentrated, and that generally is going to be tough on plant species. There's some that will thrive. Salt cedar is one. Things that tend to have very small leaf area and probably gray in color. So there's that. From the reclaim standpoint, we're seeing that across the country, across the world. In the Arab world, some of the large cities on the Arabian coast they're cooled almost entirely with large district cooling systems running on what they call treated sewage effluent. Their cost of water exceeds even that of Seattle, and their only real option is to take reclaimed water back to the cooling towers.
Well, guys, you bring a wealth of knowledge here. We truly appreciate it, not only here at the University of Arizona, but also throughout our APA family of our universities and college. Henry, I know you've been traveling throughout the world. You were in Dubai recently, looking at some cooling towers there. Damien, with your experience in North America, and then also Australia. And we appreciate that very much. We have a lot more questions. We're going to go ahead and answer the questions, but Damien, you got some final thoughts before we wrap up?
Yeah, I think, Chris, the major takeaway I have since I've been living in the US is the cost of water. And when I first moved here in 2006, there was a lot of places that weren't interested in implementing water efficiency because there was no return on investment. It was very small because of the cost of water. But now that water rates are continuing to escalate, there really is now some great advantages in saving water and a great return on investment. And as I said, look into the low-hanging fruit, which we look at, is shower heads. I think faucets and hand sinks is a huge area to conserve water on campuses, as with hand sinks for hand washing and also for toilets as well, particularly on female toilets. It's a big item to look at for water use and water savings.
Thank you, Damien. Henry?
Yeah, and I think the thing that I'm left with is this concept of the energy-water nexus and how interrelated both of those are. I've spent most of my career focused on energy, and it's now becoming clear that water is closely coupled with energy, and anything I can do to save energy probably has an effect on water.
That's perfect. Well, guys, thanks again. We've run out of time and not enough time on some great questions. If we didn't get to your questions, again, we will go ahead and post those on our APA webpage in about a week or so. And so, Henry, Damien, we appreciate it very much. And again, this is APA's way of giving back to our members. We will continue doing the webinars. They have been very positive, as I mentioned in the recent member survey. And speaking of the member survey, in the very near future at one of our webinars, we're going to be reviewing the metrics, the details that came from that recent member survey. And again, webinars was one. We'll be looking at a deferred maintenance presentation as we've done in the past. And Henry, I got to say, this Lord Kelvin, I love it. You know, if you can't measure it, you can't improve it. Right. And that's what we all have to do. So we'll be looking, our next webinar is going to be on a little off cycle a little bit on September 20th. We have several different topics, again, we'll be looking at. We also have Gary Gleason, who will be doing a steam boiler overview. Excellent topic. We had Gary recently out here. ASHRAE, we continue the partnership. Had a great call with them this morning on a number of initiatives that APA and ASHRAE will be partnering on over the next 3 years. And again, we'll be looking at the APA strategic initiatives and the realignment of our committees. And that will be discussed in detail at a future webinar also. So these webinars are good for CEUs. Henry, Damien, thank you very much. And thank you, everybody, for joining. We had a really, really large crowd. Thanks, everybody. Bye.